Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're very happy to have Sai Krishna visiting us today and yesterday. Sai Krishna is a grad student at UCLA, and he's going to tell us about some work he's done on verifiable functional encryption.
Thanks, Melissa. So hi, everyone. My name is Sai Krishna. I'm from UCLA. I'm going to talk about verifiable functional encryption. This is joint work with Vipul, Aayush, and Amit. So before we get to what is verifiable functional encryption, let's think about what is classical encryption again. There is some person, Bob, who has some input X, and he encrypts it and sends it to some cloud. Now, if the cloud does have some secret, then he can learn the value X in the clear, right? And suppose the cloud does not have this secret, then he learns nothing at all. The cloud learns nothing at all about what is hidden inside the ciphertext. This is the guarantee that we want from classical encryption, right? In some sense, looking at it a bit more philosophically, this is something like all or nothing. It says you either learn everything about what's hidden inside the ciphertext or nothing at all, right? So to broaden the goals of encryption, the notion of functional encryption was introduced by Sahai and Waters, and the goal is to give more fine-grained access to encrypted data. So how does it work? Let's say this is the same person, Bob, who has some input X, and he encrypts it and sends it over to a cloud. And now the goal of the cloud is not to learn X in its entirety, but to just compute a specific function f on the value X. Okay? And how does the cloud do this? It talks to another trusted party, a party that has a master secret key that is used to generate everything in the system. And it tells the trusted party that I want to compute this function f on any ciphertext that I receive. Now, after this, the trusted party returns to the cloud a secret key corresponding to this function f. And using this secret key for f and the encrypted message, it can recover the value of the function applied to the message hidden inside the ciphertext. Okay? So is that all? We definitely want some notion of security, right? What would we want? If this cloud is malicious, Bob does not really trust the cloud and does not want the cloud to learn everything about his input X. He just wants the cloud to learn the value of the function alone, right? So the security guarantee intuitively, what we want is that the secret key for the function f, which I'll denote as skf, should not allow the adversarial cloud to learn anything about the ciphertext except for the value f of x. Okay? We'll formalize this a little more later in the talk, but intuitively, what we're trying to say is that only f of x is given to the cloud. This is as good as Bob not giving the encryption of x, but rather just giving in the clear the value f of x, right? So this is notion of functional encryption.
But who gets to decide those function f?
Sorry?
Who decides what this function f is?
So the cloud can choose whatever function it wants, and if the trusted party feels that the cloud is authorized to learn the value of this function f, it returns a secret key for f. But if the function is just, say, the identity function, and the trusted party thinks this is a bit too much for the cloud to learn, then it does not give back the secret for f.
Right? So in what kind of form is this function typically expressed?
So it can be expressed in multiple ways. The most standard way of expressing it is as a circuit with AND or NOT gates, but you could also maybe express it as a RAM program or any other model of computation that you have in mind. So functional encryption is a pretty general primitive. It's a generalization of several well-known primitives that we have studied, like ID-based encryption, predicate encryption, searchable encryption, and so on. So before we get into more detail, let me formalize the syntax in a functional encryption scheme. There is an initial setup algorithm that generates the master secret key and the master public key. This master secret key is given only to the trusted party. Rather, this setup algorithm is run by the trusted party. And the trusted party gives this master public key to everyone in the system. In particular, the person Bob that we were talking about gets this master public key. Now, whenever anyone wants to encrypt their data, they run the encryption algorithm using their message X and the master public key to produce a ciphertext. Okay. Now, whenever you want to produce a secret key for a function f, you run the key generation algorithm that takes a function f and the master secret key as input and produces the secret key for the function as output. So, if you look back at the previous example, this algorithm is run by the trusted party who has the master secret key with itself, but the function is fed from the cloud. So, the cloud gives the trusted party the function, and if this function is something that the trusted party thinks the cloud should indeed learn a secret for, then the trusted party runs this algorithm on the function f and the master secret key to produce the function secret key. And now there is the decryption algorithm that is typically run by the cloud in our previous application, where it takes a ciphertext and a function secret key as input, and it decrypts the two to recover the value f of x. Okay. Now let's try formalizing the security notion that we wanted. Let me call this notion as message privacy. Why do we call it as message privacy? Because you want to hide the message that is inside a ciphertext, right? Let's just think back to the notion of classical encryption. What would we want? We want to say that there is a person, Bob, who has encrypted his input and sent a ciphertext that contains X inside it. And the same person, Bob, in a different world altogether. So, in the left world, he just encrypts X and sends. In the right world, he encrypts Y and sends. And if he really wants a ciphertext to hide what is being encrypted, he wants the cloud to not know in which world he is interacting in. So, the adversarial malicious cloud should not know whether it's interacting with Bob who has encrypted X or with Bob who has encrypted Y. Intuitively, the cloud does not know which of these two worlds it is in, then the message is safe, right? Because nothing about this message is known from the ciphertext. So, this is the popular, well-studied security notion for encryption. Can we just retain this? Can we just say the adversary should not distinguish between the left and the right worlds? Clearly not, right? Because in the left world, he learns f of x, and in the right world, he learns f of y. And if they're different, he can obviously distinguish which world he's in. So, what would the next natural generalization of this be? If f of x is indeed equal to f of y, then the adversary should not distinguish whether he's in the left world or the right world. Because if f of x is indeed equal to f of y, then we're saying that the only thing he does learn is the value of the function. And if once he learns the value of the function, he learns nothing else about the message that is hidden, right? So, this is the notion of message privacy. And this is a very simplified version where I said there's just one ciphertext that is being encrypted and just one function key that the adversary has. We could generalize this to say that the adversary gets secret keys for several functions, f, g, h, and so on, and he gets ciphertext for several messages, x, x1, x2, x3, and so on. And we would want the same kind of guarantees to hold. For every function secret key and every pair of messages in the left and the right world, the output of the function should be the same, right? But it's probably useful to just think about this simple scenario of one function and one message for the rest of the talk. So, what is one practical use case of functional encryption? Let's consider a scenario where there is an auditor, potentially malicious, who's tasked with the job of auditing several banks. And let's assume the World Bank is the trusted party that all banks across the world trust. And now this World Bank has a master secret key. And whenever a bank with some input X is required to be audited, it encrypts its input and sends it to the auditor. And the auditor now requests the World Bank for a function f and gets back a secret key corresponding to this function f. This function could be doing some sanity checks and checking whether everything in the bank's data was correct. And it learns the value f of x, right? And since the auditor could be malicious, we want the guarantee that the auditor should not learn anything at all about the bank's private input apart from the value f of x. Right? So, this is one practical application of functional encryption. But is there any drawback in this? So, we consider the scenario where the auditor is malicious, but what about a poor, honest auditor who really wants to do his job correctly, but due to some unforeseen circumstances, he is not able to? What does that mean? Let's say there is an honest bank that encrypts its input x and sends it to the cloud, and the auditor, after getting a secret key for the function f, learns the value f of x. All right, he's happy. Now there's another bank. Clearly, there are multiple banks in the world. So another bank comes up and encrypts its input y and sends it to the cloud. But this bank and the World Bank could somehow collude. Maybe they have some agreement and the bank says, I'll give you some money if you can hide my data. Okay? And the poor auditor who intends to learn f of y does not learn f of y, instead ends up learning g of y for some different function. So how could this happen? Maybe the value y was not correctly encrypted, or maybe the secret key for f was not correctly generated. It may not really be a secret key for f. It could be some convoluted function that says if the input is not y, output f of input, but if the input is y alone, output g of input, right? Because the World Bank, who we thought was a trusted party, is probably not really trusted, right? So what's the issue here? The issue is, in traditional notion of functional encryption, we assume that there is this trusted party who generates the master secret key and so on, but why do we really trust them, right? So consider another, yeah.
Does the problem get a lot easier if the trusted party is actually trusted, but only Y is malicious, or only the bank is malicious?
I think it will get little more simpler if the trusted party is indeed trusted, but yeah, I can get to that. So the as Melissa pointed out, the more interesting scenario is where the trusted party is not really trusted, because once you do have a trusted party generating those systems, you could always ensure that using some additional work that everyone encrypts the data correctly, or that they are really encrypting something valid. You could compile it with some zero knowledge proof. So what's another drawback? Let's say there's just one bank and all the banks were honest. Okay, so the banks are not doing anything malicious, or maybe they want to do something malicious, but probably not. Again, it just encrypts as input X and sends it to the cloud. Sorry, the auditor. But now the auditor who wants to learn two functions, f and g, gets back secret keys for f and g, supposedly. But instead of learning f of x and g of x, he learns f of x and g of x prime or x double prime for some arbitrarily different message, right? All he has is just a ciphertext and a function key, and he does not know the message inside the ciphertext. So he has no way of telling whether what he did get was g of x or g of x prime for a different message, right? So the poor auditor is lost and he believes he is doing his job correctly, but apparently not. Okay. So what do we want out of this? We want to add the notion of verifiability, right? This is not something new. It's been there in crypto for a while. We want to tell that everyone is doing whatever they were supposed to do correctly. So how do we formalize it a little more? Let's say there is some person who gets some ciphertext out of the blue from somewhere. He wants to run a publicly verifiable algorithm that takes the ciphertext as input and tells whether this is a valid ciphertext or not. Okay? It takes a ciphertext and it does not tell what the message inside the ciphertext is, but it just tells you that the ciphertext was honestly generated according to the encryption algorithm. Okay? So he's happy now that he has a good valid ciphertext that no one tried to cheat him with. Now let's say he gets a function secret key, supposedly for function f. Now he wants a guarantee that this secret key was indeed for the function f that he has in mind. He again runs a different public verifiable algorithm that takes the secret key and the function f as input, and again tells whether this is a valid function or not, valid function secret key or not. Okay? So now he is happy. He has a valid ciphertext, a valid function secret key, and he can decrypt both of them to recover f of x. Okay? So just to put it in a little more formal terms, verifiability states that for all master public keys generated in the system, for every valid ciphertext, what do I mean by valid? That there is a public algorithm that will output given a ciphertext whether it's valid or not. Inside every valid ciphertext, there exists a unique message X that is encrypted, such that for every function f and every valid function secret key, again by valid I mean that you can test its validity with a very publicly verifiable algorithm. If you decrypt this valid ciphertext with this valid function secret key, you will get the output to be f of x, where x was the message hidden inside the ciphertext. In particular, if I decrypt CT with SKF, I would get f of x, and if I decrypt CT with SKG, I would only get g of x. I would not get g of x prime. This is the guarantee we want. Yeah.
So here, when you a valid ciphertext is just you don't know what message it's in. You just know there's what message is in it. There's just some message.
Exactly.
A valid key is valid with respect to a particular function.
Not necessarily. It's enough to say that a valid key is valid with respect to just being a valid function secret key. So once you know that it's a valid function secret key, you could always test whether it was the function secret key for the function you had in mind.
How do you test that? That's the second sort of.
Since it's a public key encryption, since it's a public function encryption system, I could encrypt a dummy message myself and then just decrypt my dummy ciphertext with this function secret key to see if I get back f of that message.
Although there presumably are functions that where it's hard to find the differing input or something like that.
Point function.
No, but I know for sure that this is a valid function secret key.
Mm-hmm. But so if you know that it's a valid function secret key for some circuit, but in order to tell if it's exactly this function, you might have to probe it on all inputs. Or
Right. So,
like that.
all right, that's a good point. So maybe we can think of it as to test validity for a function secret key, you need the function also as input. So the validity box would give back a tick only if the secret key is indeed a secret key for that particular function. Okay. Yeah. So I guess that would address the problem. Right. Okay. Should I move ahead? Okay. So let me briefly describe the results that we obtain. If you remember the security notion for message privacy, it was what we would call an indistinguishability based security notion, because we said the adversary should not be able to distinguish whether he's in the left world or the right world, right? So there is another stronger notion of security, which I'm not going to get into details about, which follows along similar notions considered in crypto, called the simulation security, but we show that simulation security in general for verifiable FE is impossible to achieve. And then we show that given any public key message hiding functional encryption scheme, you can generically transform it to a verifiable one with not too much additional work. Okay? This is the main result that I'm going to be focusing on for the rest of the talk. In addition, we also give generic compilers for the case of secret key functional encryption that also have function hiding along with message hiding, and also for the more general notion of multi-input functional encryption. We use the same techniques to achieve verifiable obfuscation. I'm not sure if I'll have enough time, but I'll try to cover that briefly. Where even in the, to just put it in a couple of lines, even in the context of obfuscation, if someone gives you an obfuscated code, you really don't know what's in the code. So you want some guarantee that the correct code was obfuscated. So to address that concern, we put forward the notion of verifiable obfuscation and give and initiate the study of that area.
Doesn't that contradict the goal of obfuscation that you can't tell if
Exactly. So there is a lot of modeling issues that arise. So the way we try to address that is by saying that the obfuscated code would satisfy some particular public predicate. So you just have a guarantee that your obfuscated code satisfies a given predicate, but you don't know which circuit it essentially obfuscates. Does that answer the question? Okay. And then we give an application of verifiable FE outside the context of functional encryption to this new notion of functional commitments. So just to tabulate our results, so remember I told you that FE is a generalization of ABE, IBE, predicate encryption, and so on. So you take any well-known scheme for predicate encryption, ABE or IBE, and you can easily transform it to a verifiable one with not too many additional assumptions. In particular, the only assumption we need in addition is the DLIN assumption over bilinear maps, and note that most constructions anyway already implicitly require this assumption. And we also have another result that shows that if you do have a verifiable function encryption scheme, it implies having DLIN assumption. So I'm not going to get into details of that. So is this a trivial problem to solve given any? Let's get back to the case where we have a public key functional encryption scheme with message hiding, and we just want to make it verifiable. Is this really a trivial problem to solve? So let's say we have a setup algorithm, and here is our new encryption algorithm for the verifiable FE case. Given any message as input, encrypt the message as you would encrypt using the original public key FE scheme. So the red ciphertext corresponds to a ciphertext in the public key FE scheme that we want to transform. Okay. Now you just compute a proof that this was encrypted correctly. What proof is it? In particular, let's use a zero knowledge proof. Okay? A zero knowledge proof is just a proof that tells that nothing at all about the statement you're proving is going to be revealed. Okay? And now the ciphertext is just going to be that here is the encrypted ciphertext with the old FE scheme and the proof that it was encrypted correctly. Now everything seems to work fine, right? But unfortunately, this wouldn't work, because in order to generate this so-called zero knowledge proof, you need something which is the common reference string in your setup, right? But who runs the setup? The setup is indeed run by the authority, and the whole point of verifiability was in the case where the authority is not trusted. So if the authority is believed to be trusted, then he could generate the CRS, but this is a circular problem, right? So clearly just adding a zero knowledge proof would not work. But though it's a trivial failed attempt, it offers quite a lot of insight into how we could approach this problem. Notice that the only thing that didn't work here was that we needed something special in the setup, right? As long as you didn't need anything in the setup, if you could give a proof that everything was done correctly, then you're done. So let's switch to a different kind of proof system, which we call witness indistinguishability. I'll explain what it is just for sake of completeness a little more clearly. But the crucial point about witness indistinguishable proof systems are that they don't need anything in the setup. Okay? Anyone can publicly run it without having to program the setup to have anything special. So what is of the witness indistinguishable proof that we will compute? It will just say that a witness indistinguishable proof in general just says that when I'm proving a given system, either of two witnesses could have been the way to prove that statement. Okay? But the proof does not tell you which witness was used. So let me explain it in the context of our scheme. Let's say we had the same public key FE scheme that we started out with. Let's run it twice. Okay? The red master public key and master secret key are the first run, and the green ones are the second run. Now, whenever you want to encrypt a message X, you compute the red blob first using the first master public key, and then the green blob using the next master public key, and give a proof that says that either the red blob encrypts X correctly or the green blob encrypts X correctly. Okay? This proof would not tell you whether the red blob did encrypt X correctly or the green blob encrypted X correctly. It just tells you that one of them did encrypt it correctly and not which one. Okay? Yeah.
And those aren't necessarily like the same X. Is that true?
Sorry?
The two X's aren't necessarily the same, is that right? So.
Oh, it is the same. It's the one that was fed as input to the encryption algorithm.
But the statement for the proof, it doesn't have X in the clear, right? That's hidden, or is it?
Right. Sorry. The statement doesn't have X in the clear. X is part of the witness.
Okay.
Does that make sense?
Yeah. So there exists an X such that I know this
Exactly.
red thing encrypts X or
Yeah.
green thing.
Yeah. So the statement would just be that the proof is valid, and the witness for that would be the X that was encrypted either in the red blob or the green blob, and the associated randomness that was used to encrypt. Okay? So now you just give a proof that one of them was encrypted correctly. And let's do the same thing in the case of the function key generation. We generate two function secret keys, one with respect to the red master secret key and one with respect to the green master secret key, and just prove that at least one of them was generated correctly as a proper function secret key. So would this work? Does this easily solve the problem? Not really, because let's say the red encryption was done correctly with respect to the red blob, and function key generation was done correctly with respect to the green blob. How would you decrypt such a system first? I haven't explained the decryption algorithm. Given the red blob and the green blob, for the ciphertext, and a red blob and a green blob for the function key, you would decrypt the red ciphertext with the red function key to generate some f of x prime, and you would decrypt the green ciphertext with the green function key to generate some other f of y prime, right? And now you have no idea which is what. How would you pick which of one of these two to be your actual output? Just see if both of them are equal, and then pick that to be your output. Okay? To just explain it a little more clearly, you have a red ciphertext and a red function key. Decrypt the two together to obtain one output. You have a green ciphertext and a green function key. decrypt the two together to obtain one output. And if both of them do match, then output that as the final decrypted value. If that is the way we're going to proceed, then clearly this would lose verifiability, right? Because if you decrypt the red ciphertext that was encrypted correctly with a wrongly generated function key, you will not get a valid function output. And similarly for the other case. So what does this tell us? This tells us that verifiability intuitively needs a majority of systems to be correct on either side, right? Okay, so maybe now let's use 3 systems for the underlying FE scheme, a red, green, and a blue one, and repeat the whole process. What would the ciphertext prove? It would prove that 2 of them did encrypt the same message correctly. And what would the keys prove? Shall we prove that all 3 are keys for the same function? In which case, we know that at least a majority of the red, green, and blue ciphertext would have corresponding function keys that do match, right? But then, if we do go ahead with this approach, we can't argue message privacy, because the minute we prove that all 3 functions are indeed bound under the same system, we cannot switch the message from an encryption of X to an encryption of Y. Right? Because in order to be able to switch the encryption of X to an encryption of Y, we need this challenge ciphertext to come from the outside, from another challenger. The reduction would not be able to generate it itself, but the reduction would have to generate a proof that the third key was correct. So inherently, message privacy is not going to be easy to argue. So instead, can we just show that 2 of them are correct function secret keys? Why would we need all 3 to be correct? We just have a majority correct that side and a majority correct this side. Would this work? Not really, because how would a decryption procedure work? A decryption would say that decrypt the 2 red blobs, decrypt the 2 green blobs, decrypt the 2 blue blobs, and see if a majority of them are correct. What if the encryption algorithm proved that the red and the green ones were correct, and the decryption algorithm proved that the green and the blue ones were correct? Sorry, the function key generation algorithm. Now when you decrypt, it's only the green blobs that match, right, on both ends. The red and the blue ones don't match, and they're going to produce faulty outputs. So you will not get a majority equal correct outputs. So what is, yeah?
So you're not okay with just detecting that something went wrong, you actually want to get the right answer.
Sorry?
So you can imagine, I think this is weaker than what you're saying, where you want that if somebody's done something, either you get the right answer or you can tell that somebody screwed something up.
Exactly. So with this approach, as you pointed out, you can either get that the decryption algorithm is perfectly correct, it outputs f of x, or you're happy with the decryption algorithm, just output bot, saying that someone screwed it up, but you don't know who. But we want something stronger. We don't want anyone to screw up. We want everyone to be correct, and that is not solved by this, right? So what is the main bottleneck in this approach? It looks like verifiability and message privacy are 2 contrasting things, right? Verifiability says I need a majority of large systems, a large majority of systems to be correct, so that when I decrypt, I get a good majority of systems to be correct on both sides, in the case of the encryption and in the case of the function keys. But message privacy intuitively says you need some amount of free system so that you can switch them from encryption of X to encryption of Y. Yeah.
Is it obviously why you need a majority?
For
the privacy?
Oh, for the privacy?
Decide which output is correct.
But that's for the verifiability part, right?
So, if we look at it here, maybe right now it's not obvious that for message privacy you need a majority of free systems, but let's say we need at least a good fraction of free systems so that you can switch, right? Or at least one free system to be able to switch. So let's go ahead with that. We need at least one free system to be able to switch. 3 parallel systems didn't seem to work. Would 4 work? Again, it seems difficult because even the notion of majority in 4 is not well defined. Do you go with 2 or do you go with 3? So let's go ahead and start with 5 systems. Okay, I'm not going to list out the colors, but you can see that there are 5 different systems out here. And now in the encryption algorithm, we prove that at least 4 of them encrypt the same message, X, or just 2 of them encrypt the same message, and all of them are committed in this public parameter Z. Okay, we introduce a new parameter Z in the public parameters, and just prove that all of them are locked together there. Okay? The minute you generate the proof, somehow all of these have just been locked together in this public parameter. It seems not really useful right now. Okay? But let's see how we can leverage the fact that they're somehow hidden in this public parameter. To generate a function secret key, you either prove that 4 of them are keys for the same function f, or you prove that 4 are keys for the same function f, and if you look at the public parameter that had 5 small ciphertexts inside it, and you decrypt, now you open up what was inside the public parameter, it had 5 blobs inside it. You decrypt each blob with the associated function blob that you have generated here. This proves that the decryption of each of those 5 blobs is going to be the same. Okay? So what does it say? It doesn't say that some of them are going to be same or 3 of them are going to be same. It says this public parameter that you have fixed, if you open up the ciphertext inside it, everything is going to decrypt to the same value. Okay? Yeah.
It looks like the 2 cases, like the second case on the right-hand side is like strictly stronger than the first case.
Exactly. It is indeed strictly stronger than the first case. So I'll explain later why we need the 2 cases separately. But yeah, for now it does seem like the first case is redundant. So let's assume the first case was not even there.
So here it seems like a prover could always just prove the first case. Because if either one of them is true, the first one will be true. So we have to always prove that. Is that right?
Right,
Okay.
that's true.
Okay.
So a malicious prover could always do that, but an honest prover would want to use the second case to get a little more against a malicious verifier. Maybe it'll become a little clearer when we try thinking about how do we argue security. Okay, so let's ignore verifiability for a minute and just argue message privacy. My claim is this system already satisfies message privacy. And the way we would do that is, let's say we had to encrypt the message X, and we encrypt X in all the 5 blobs. And the goal is to now change every X in the tuple of 5 to an encryption of Y. Right? We want to switch from an encryption of X to an encryption of Y. So initially, let's say we prove that 4 of them encrypt X correctly. And we prove that 4 of these are keys for the same function f. Okay? This is our starting point. Now we switch to say that 4 of these are keys for the function f, and this additional condition that if you look at the public parameter, all of them would decrypt correctly. So what would we place in the public parameter? We would place the commitment to all the 5 blobs that are generated in the encryption algorithm. Okay? We would now switch the encryption algorithm to use the trapdoor statement that says that only 2 of them encrypt X correctly. It would be the first and the second system alone. Okay? And what would the function key prove? It would just prove that the first 4 indices are keys for the same function f. So now look at the 5th index. The 5th index need not encrypt X correctly and need not generate a key for f correctly. We're not going to use the fact that we know how the 5th index was encrypted or how the 5th function was generated, the 5th function secret key, right? So in the 5th index, we can easily switch from an encryption of X to an encryption of Y, right? And now we would repeat the same process. We would prove that the 4 keys are keys for the indices 1, 2, 3, and 5, okay? And we would switch the 4th index to have an encryption of Y. And then again, we would prove that the keys are correct for the 1st, 2nd, 4th, and 5th indices, and prove that the 3rd index, and leave the 3rd index to be free, and change the 3rd index to be an encryption of Y. Okay, so this way, yeah.
Here you're using the fact that f of x is f of y.
Exactly. So
The statement is true even.
the reason why we need this statement is because we're using the fact that whenever we switch an encryption from an encryption of X to an encryption of Y, f of X is indeed equal to f of Y. So when you decrypt a blob with either a blob that encrypted X or encrypted Y, we're going to get the same value, and there is no contradiction that arises. So message privacy seems to follow with some amount of work in this idea. Right, so once we've achieved this point, we can switch the last 2 indices to be the ones that are correct and then change the encryption of X in the first and second index to be an encryption of Y. So this, the high level idea I hope is clear. You can just believe me that this doesn't need too much amount of work. But clearly verifiability is not maintained here, right? It's look at the scenario where a ciphertext was proved using the second statement and a function key was generated using the first statement. Now, if only 2 of the 5 blobs are encrypted correctly, then you cannot hope to achieve a majority of correct decryptions, right? So what is the problem here? If the ciphertext was encrypted according to the second statement and a key was proved according to the second statement, then we are fine, because the public parameter says that the decryptions would work out correctly. But the only problem arises where the keys are proved using the first statement. So the 2 tick marks that are shown, these are the only ones that pose a problem to achieve verifiability. So let's just add another lock and say that these 2 things cannot occur together. So we will add another parameter in the public parameters called W and say that if you wanted to prove the ciphertext was encrypted correctly using the second statement, then you would additionally prove that W is a commitment to 1. And here, in the case of the function keys, you would additionally prove that W is a commitment to 0. Now note that these 2 together can never occur, because if a proof was valid and it proved that the second witness was correct for the encryption, it necessarily proved that W is a commitment to 1. And if it's valid and proved that the first witness was correct for the function keys, it necessarily proved that W is a commitment to 0, and they cannot occur in tandem. Right? Yeah.
So you're going to talk about why you need that first case at all on the right-hand side? Like, did you use that in the first sample?
Right. So right now we didn't use that in the proof at all. You could have essentially had only the second case to go ahead with the entire proof. But something that I'm not going to mention why it's needed is the next goal is to actually transform any secret key functional encryption scheme to a verifiable one that also has function hiding. In that scenario, note that okay, I'm not sure how to bring out the intuition for that, but the first statement would really be useful. And in order to prove function hiding along with verifiability, the issues arising would be the same as proving message privacy and verifiability in the public key context. So the idea is to mirror whatever we did in the public key context in the secret key context as well. So in the public key context, note that the free statement in the ciphertext just says that 4 of them encrypt X. Now in the secret key case, you want to say that function is hidden. So in order to mirror that, you want to say that 4 of them are keys for F. So maybe intuitively you can think of just extending the system a little more, having a few more witnesses to say that the secret key system has message privacy, function privacy, and verifiability. Okay. Yeah, maybe should I stop? Okay. So let me briefly tell you a result for verifiable obfuscation. So what is indistinguishability obfuscation? Let's say we have 2 machines that are functionally equivalent. Then indistinguishability obfuscation, or IO, states that if you do obfuscate the 2 programs separately, then an adversary cannot distinguish between these 2 obfuscations as long as the 2 obfuscated circuits were functionally equivalent. Okay? So given 2 functionally equivalent circuits, an adversary should not know which of the 2 was indeed obfuscated and given to him. But again, the same issue of verifiability arises here. How do we know that the correct circuit is indeed obfuscated? In most applications of IO, you trust someone else to give you a correct obfuscated circuit, believing that they indeed did obfuscate a correct circuit. Right? So you want to not really trust them entirely, and you want some guarantee that they indeed obfuscated the correct circuit. So this is the notion of verifiable IO, and let's look at a trivial scheme and see whether this would work. Let's say we have an IO scheme to start out with, and we want to obfuscate a machine M. Let's obfuscate it 3 times using our original IO scheme, and just compute a proof that 2 out of these 3 obfuscate functionally equivalent circuits. Okay? In order to evaluate such an obfuscation given an input X, you just verify the proof, see if the proof verifies that the obfuscation is valid. then evaluate each of the 3 obfuscations and output a majority of them. Okay? If the proof just told you that at least two of them were equivalent, then clearly when you evaluate them, at least 2 of them are going to give you the same output. Yeah.
So here you're just trying to prove that this obfuscates some circuit, not like any property of the circuit.
Right. So this, just obfuscates some circuit.
I guess according to the legal or the
Right. So you need to add some properties as to what you really want to obfuscate, but that's not going to be too hard because your proof could additionally just prove that each of these obfuscated circuits satisfy some predicate that is well known publicly, right? And trivially, verification follows because if 2 of the 3 obfuscations were correct, then a majority of the evaluations would work. Note that there is no problem as in the case of FE here because the input that you evaluate with is always correct. You're the evaluator. There is no common majority of systems that have to be correct. Just a majority of obfuscations have to be valid, right? So verification is somewhat free, and security is not too hard to achieve either. So you start out with obfuscating M0, 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 and you want to go ahead finally to a system that obfuscates M1. So you switch the last obfuscation to be an obfuscation of M1. Then you switch to prove that the second and the third ones obfuscate functionally equivalent circuits because that's what we want to prove. Then you switch the first system to obfuscate M1. Then you prove that the first and the third ones obfuscate equivalent circuits, and you change the second system to obfuscate M1. Right? So it seems that security should easily follow. Yeah.
is the statement that 2 circuits are functionally equivalent, is that like an NP?
Exactly. So notice that the only issue that arises here is that proving that 2 circuits are functionally equivalent is not an NP. The only way I can prove that 2 circuits are equivalent is if I run it on all possible inputs and show you that on every input they give the same output, but that's clearly not an NP. So this approach would not directly work here, but it does work for a relaxation of I/O where we guaranteed that there is an NP language that tests equality, right? So this is the main idea, and now what's left is just some modeling issues about what kind of circuits you can hope to obfuscate and whether they give you reasonable applications.
You get to choose the circuits, though, to some extent, right? These aren't arbitrary circuits.
Right.
So you could choose circuits that can be efficiently shown to be equivalent.
Exactly, right. So as you pointed out, in traditional applications of I/O, you obfuscate specific circuits, and it's not too hard to show that those circuits have a small witness of being equal. Right. Yeah, with that. Yeah. Any questions?
Are there any additional questions? Just one quick question. So you were saying everything you can do with DLIN in the first half?
Right.
Is that all that using Sahai?
Exactly. So to obtain the NIBI, we need DLIN from Graz.
So it doesn't have to be at all related to the actual underlying functional encryption.
Right, it doesn't.
So it could be any NIBI, it's just that that's like one way.
Exactly. So if I go back to the table, if you do have an IBE scheme or predicate encryption scheme that just arises from discrete log or let's say DDH, then you would need DLIN as an additional assumption. But if you have some IBE scheme that already requires DLIN or something worse, then you don't need any additional assumption.
Or in the first case, you could use, I don't know what else we have for efficient schemes, but something based on.
Right. So DLIN is just assuming you don't have any better ways to generate values.
Any other questions?
So can you tell a little bit about what kinds of functional encryption schemes are there?
Right. Maybe I can explain it with the table. So there is an IB scheme that first came out in 2003. There are a lot of schemes for predicate encryption, attribute-based encryption. There is functional encryption that just tests whether inner products are equal. Then there is functional encryption that computes inner product. There is functional encryption for all circuits. There is functional encryption that just takes 2 ciphertexts as input and computes functions on 2 inputs. Then there is the most general notion is this multi-input functional encryption that can take arbitrary ciphertext and compute a function on arbitrary number of them.
What is OWF? Injective OWF in the last one?
Oh, sorry, OWF is just one-way functions.
Okay.
But the first thing is indistinguishability, obfuscation, IO.
Yeah. Okay.
So does that answer your question a little detail?
How I mean, there's probably like huge efficiency differences in.
Right. So the more general class of functions that you want, the less efficient it gets, and it requires more heavy hammers, larger crypto tools. But if you do want something very simple, like just testing inner product being equal, or just maybe even computing inner products, then you can do that quite efficiently.
What is the DLIN-based functional encryption? The third from the bottom. The SS10 and
SS10 is Sahai and Kansayoli Blue, and GBW12 is Hoitek, Vinod, and Sergey. So this was the one where they also, I think this is the paper on reusable Gabel circuits and FE for bounded collusions. So they just show that you can get FE for all circuits as long as the number of function keys that are asked by the adversary is bounded.
In the, I guess, the common reference string, if you brought that back, does like the obfuscation stuff become easier too? Okay, so you're saying that like the proofs, you can't do the proofs, the zero mode proofs without the common reference string. I guess for the IO.
Right. Oh yes. Yes.
Similar.
If you have a common reference string,
Yeah.
then you don't need the fact that you have a short witness to prove. You just obfuscate a circuit once and give a proof that your obfuscation was correct.
Thanks. Yeah.